All right, first thing talking about today is what this reaction quotient is. Basically what it is you're calculating the reaction quotient to figure out if a reaction is at equilibrium or not. And then once you figure out if it's at equilibrium or not, it will tell you also like which direction the reaction has to move in order to reach equilibrium. And so, I mean, the cool thing about calculating Q is it's the same as calculating K. You set up the expression the same way, you plug in values, whether it's pressures or concentrations. The only difference is that the pressures and the concentrations you're given are not necessarily equilibrium concentrations or pressures. So, again, it tells if the system is in equilibrium and which direction it has to go to reach equilibrium. Okay, so here's my example. I've got H2O, Cl2O. These are all, I should have these all labeled as gases so that we know that they're all supposed to be in the expression. The K value for this is 0.090, and I should also specify here this is Kp. Because the question then will be, is the system in equilibrium when? And they give me all of these different pressures in torr. And it doesn't matter, they don't have to be in atmospheres. You can plug them in torr as long as they're all the same. So if I write out my expression for Q, and I'm going to put a little p next to it just to specify that it's being calculated with pressures and not concentrations. Okay, that expression is going to be the pressure of HOCl squared, because that coefficient is 2. So products over reactants is all I'm doing. And then the pressure of H2O. And then also on the bottom, the pressure of Cl2O. And they give me all the numbers right here. So I just plug those in. So I get 21 squared, 200 for the pressure of the H2O, and then 49.8 for my pressure there of the Cl2O. I calculate that Q value. That Q value is 0.0443. What you want to do is once you calculate that value for Q, you want to compare the Q value with the K value. Okay, and I'm going to decide, is it smaller or is it bigger, and then what does that mean? So my Q value, is it smaller than or bigger than K? Smaller, right? Okay, so Q is smaller than K. Okay, so first of all, what that tells me is that if these are the pressures of all of these gases in this equation, it tells me that since this number is smaller, these pressures are not at equilibrium. So that reaction has not reached equilibrium. It doesn't have the forward reaction and the backward reaction happening at the same rate. And so the concentrations of everything and the pressures of everything are not going to stay the same over time. So now I've got to figure out what has to happen in order for the reaction to reach equilibrium. If Q is smaller, and I mean just think about the general idea of these Q and K values is that it's products over reactants. So if Q is a smaller number than K, which did it have more of, products or reactants? More reactants, right? So because Q was smaller, I don't know if too many is like the right wording, but the idea is that there's more reactants than there should be at equilibrium. So if there's too many reactants, I need to make, that reaction needs to make more products, or you put more products needed or something like that. So the forward reaction has to speed up in order to reach equilibrium. Okay, so all of those things you have to be able to tell just from calculating that Q number. Q is too small compared to the one at equilibrium, so I know I had more reactants than I would normally have at equilibrium. So more products need to be made so that the reactants get used up. So that forward reaction has to speed up. The forward reaction speeds up because that's the one that's going to make more product and use up the reactants in order to reach equilibrium. Okay, so that's what you're going to tell from calculating Q value. It's kind of all of that information. All right, questions on that? All right, the rest of our examples today are all this question. Well, it's either calculating equilibrium concentrations or calculating K given different information. So I'm going to let you guys write down this example, and then we'll go through the process of how to solve it. All right, all of the problems that we're going to do the rest of today and in the rest of chapter 13 and also in 14 and also in 15 require to use this procedure of setting up what's called an ICE table. The I, the C, and the E all stand for something, so it's like an abbreviation. We'll talk about what all those things stand for. So in this question, we've got the reactants, the products. They tell us some information, and so we'll kind of put that into our chart when we set it up. So it says there's 4 moles of NH3. It's introduced into a 2-liter container. Basically, all that means is they took 4 liters of NH3, they put it in a 2-liter container, they sealed it, okay? And they let that NH3 decompose and turn into nitrogen and hydrogen. And then you've got this double arrow going, and so it's going in both directions. Okay, we've talked about that. At equilibrium, 2 moles of NH3 remain. We started at 4. What's the value of K for this reaction? Now, setting up the ICE table, it always helps to have your reaction up at the top. So if you need to rewrite the reaction, rewrite the reaction. And for now, label these letters. As you get the hang of setting up an ICE table and everything like that, it becomes a pretty automatic thing. But we're going to set it up vertically. All of the I represents initial concentration. Okay, so the I represents initial, that's where that comes from. The C represents the change in the concentration, and the E represents the concentration at equilibrium. Now, we don't know all of these numbers, but we're going to go through and kind of see what's going on in the reaction. So you set it up like this, and you actually want to draw all these lines so that you keep all of your information separated. And you want to go through and you want to fill up the rows, top to bottom, and using all or any of the information that I'm given. Okay, so the first thing I want to do is I want to fill out the initial concentrations of everything. That means like before the reaction begins, what do I have? Now it tells me I have 4 moles of NH3, and I put it in a 2-liter container. So my initial concentration is 4 moles over 2 liters. That's 2 molar. That's my initial concentration of NH3. Before the reaction is allowed to proceed at all, what should my concentration of N2 and H2 be? 0. Okay? This is usually going to be the setup with zeros over on the product side, unless they specifically tell you that you start with concentrations of something over here. Okay, so I have the 0 of this to begin with. Now, when you go through the row of change, how the concentration changes, you're looking at basically the ratios based on coefficients. So as NH3 disappears, okay, so this kind of goes along with what we did in chapter 12, it's going to disappear at a rate of, negative 2x. Negative because this is going to be disappearing, and 2 because of that coefficient over here. Over on the right side, these are both going to be adding or increasing in concentration. So N2 will be plus X, and H2 will be plus how many X? 3X, okay? So that's my change row. In my equilibrium row, you basically go through, you go down your column, and at equilibrium, I'm going to have 2, which is what I started with, minus 2x, however much it loses. Okay, I'm going to have 0 plus x here, which is just x, and 0 plus 3x right there, which is just 3x. Now, in this particular problem, it tells me that at equilibrium, 2 moles of NH3 remain. So that's my equilibrium, 2 moles in 2 liters. What's that molarity? 1, okay? So this 2 minus 2x equals 1 because of the 2 moles in 2 liters at equilibrium. So and the thing that's tricky about this is that every problem is a little bit different, and every time you're given different information in different parts of the chart. So you kind of have to figure out where it goes. Now, since I know that 2 minus 2x equals 1, then I can go ahead and solve for x. So your ICE tables that you set up, you're always going to be looking for ways to solve for x. Okay, so if you have something where it gives you what it's equal to, then you can solve for x pretty easily. So 2 minus 2x equals 1. You should be able to solve for that. X is equal to 0.5. The question is asking me to solve for k. What is the value of k in this reaction? Now, k, if it's just k, then it's Kc. It's based on concentration. So, my equilibrium expression is going to be the concentration of N2 times the concentration of H2 cubed, and then over here on the bottom, the concentration of NH3 squared. Okay, so if I'm asked to solve for k, I know that I have to plug numbers into this expression. So I have to figure out what those numbers are. Well, if I know that x equals 0.5, then I can solve for these numbers very easily at equilibrium, because I have to plug in the concentrations at equilibrium. So I've got to plug in stuff from this row. So my concentration of NH3 is equal to 1 molar. Okay, that was given to me in the question. My concentration of N2 is equal to X, which is equal to 0.5 molar. My concentration of H2 equals 3x, so 3 times 0.5 is 1.5 molar. So you're just taking this x and you're plugging it in to all of the different parts of the ICE table to solve for those concentrations. These are all at equilibrium. So I can take those numbers and I can plug them into this expression right here and get a k value. Okay, so k is equal to 0.5, and then next 1.5 cubed, and then 1 squared. Yeah. Sorry. Do it like this. You need the chart?
You're good.
Okay. So then you calculate for k and you get 1.69. All right? Lots of stuff there. Any time that it is asking you, it's an equilibrium problem and it's asking you for k, or it's asking you for concentrations at equilibrium, you always have to start by setting up an ICE table and solving for x so that you can plug numbers into the equilibrium expression to solve for k. I'm going to give you another example. Like I said, the tricky thing about this is that they're all like different. So I mean, I can't do every single type of problem, and we're going to do a few.
Okay, how'd you get negative 2x on the change from?
Okay, because the 2 in front of here, and then negative because this is the reactant, so it's going to be disappearing.
Oh, okay.
So anything that's over on the reactant side is going to have a negative in front of it. Anything over on the product side is going to have a plus.
And then how do you get the equilibrium equation again?
This?
Yeah. For the 2 minus 2x and 1 for the...
Okay, so I did 2 minus 2x right here, because I started with 2, and then I'm going to disappear at minus 2x. And how did I get the 1? Because it told me at equilibrium, 2 moles were left in that 2-liter container. So then moles divided by liters gave me that molarity. Okay, good questions. Anything else about where did I get any of these numbers from? That's important stuff to understand.
Why did you get zeros for H2 and H2? For
The starting concentration, because they said at the beginning of the reaction, they took 4 moles of NH3 and they put it in a sealed container and closed it. So the initial concentrations are the concentrations before the reaction happens. So since the reaction hasn't started yet, those are zeros. That's fine. Anything else? Before we do the next one, I'm going to have you set up the ICE table on your own on the next one. Okay, you ready? All right, go ahead. You can copy down this question, and then I also want you to don't worry about any of the numbers or anything, except for this here is your initial concentration of each F. Don't worry about solving anything. I just want you to copy down this question, write out the reaction, and then I want you to fill out the ICE table. And then we'll make sure you have your ICE table filled out correctly, and we'll go through the solving of the rest of the problem. This question is different. It's asking you for concentrations at equilibrium, and it gives you the K value. If you've set up your ICE table already, go ahead and just compare it with the people at your table and just talk about it and make sure that your ICE tables match up and that you agree on how you filled it in, and then we'll see what you have. Have your ICE table filled in?
Yeah.
First row, the initial concentrations. What should I have as my initial concentration of HF right here? 2.0. Okay, they give that to me just in molarity, so that's easy. I just have to plug it in. My initial concentration of H2 is 0. F2? 0. Okay, in my change column, minus what? 2x over here plus x and plus x. So in your E column, you go down, or your E row, you go down the column and combine those together. You should have 2 minus 2x, and you should have x here and x here. Now, the tricky thing about this problem is that it doesn't give you any of these concentrations. So you can't easily solve for x. But they do give you k, and so we're going to use that to solve for x. And so you have to write out the equilibrium expression first. So k is equal to the concentration of H2 times the concentration of F2, so this is products over reactants, and then the concentration of HF squared, because the coefficient is 2. What I'm going to do is I'm going to take all of my equilibrium row and I'm going to plug it into my expression for k. So you plug in x's and everything, okay? So what I'm going to do is my concentration of H2 is x. My concentration of F2 is x. You end up with lots of x's everywhere. Okay, down here, HF is 2 minus 2x, and that's squared. Since you're dealing with so many x's, you're trying to solve for what x is. You want to try and simplify as much as possible. So simplifying this would give me x squared over 2 minus 2x. That gets squared. Now it's equal to k. They gave me my number for k in the problem right up here, 1.5 times 10 to the negative fifth. Okay, so it's not always easy, but you can solve for x. So what I can do here is, and again, you want to look for things that you can simplify. Since this is squared and this is squared, if you can get rid of squareds, then that makes everything a lot easier. So if I square root both sides, then I'll get x over 2 minus 2x equals whatever the square root of is 1.5 times 10 to the negative 5 is. And you can just plug that into your calculator. And getting rid of that takes care of you having to do any kind of quadratic formulas. There are problems of these where quadratic formulas are required. The good news is that the AP test never makes you do that. They always give you ones that are simple enough for you to either simplify or to use another strategy I'll talk about in a minute. Okay, so you should be able to do this and solve for x. If you can't solve for x on this, you need to talk to me, okay? X equals 0.0077. That number gets plugged back in to this because the question was, what are all the concentrations at equilibrium? So then you plug that number in for x in this entire row. So then my concentration of HF, which was 2 minus 2x, I plug in my 0.0077, and I get that concentration is 1.98. My concentration of H2 and my concentration of F2, those both equal x, just from my chart. And then, which makes both of those concentrations 0.0077 molar. Okay, so the question is, what are the concentrations at equilibrium? And those are your answers. There's like several answers. You have to have one answer for each thing in the equation.
You need the answer for F2 or not?
It's the same as H2 because they're both x. So you can kind of do this where like they both equal that, so they both equal this. By the way, the same thing would be, you would do the exact same thing if you're dealing with pressures instead of concentrations. Okay, and if you want to double check these concentrations, you should be able to plug it all back in here and get the right K value.
For this one, is it like